Hello guys, how are you doing? Just let me know if my volume is loud and clear and if we are good to go. Alright, please let me know fast. Alright then. So guys, welcome to Unacademy JEE English. This is a brand new channel by Unacademy, which is India's largest online learning platform for IIT JEE. And here everything is taught to you completely in English so that none of the students feel left behind. Alright. So today is lecture 2 of Work, Power and Energy, and this series I am hosting for 2020 aspirants. So here the focus is more on quick recap of key concepts and problem solving. Alright. So let's get started. Now, before we start, let me introduce myself one more time. My name is Rohit Dixit and I've studied mechanical engineering from IIT Delhi. I have 7+ years of teaching experience wherein I've taught at most of the big names in the industry. I myself was JEE rank 447 and I've coached many students to top ranks in IIT JEE. Alright. So moving forward, let me also tell you about the Unacademy subscription and the benefits that this one comes with. Alright. So you have live classes, you get to interact with your educators, you have live polls and leaderboards, you have test series and analysis, and you have live doubt clearing sessions. So all these plus points give you a huge boost in your JEE prep. And on top of everything else, you have access to India's best educators with your Unacademy subscription. Alright. So how do you get this amazing subscription? Follow these easy steps, install the Unacademy app, and once you've installed the app, go to the plus section, select your goal as IIT JEE and click that get subscription button. Alright. So it's that easy to get your amazing subscriptions. And if you notice that the pricing has been kept very reasonable. For a 24-month subscription, the cost is 36,000, which roughly comes about to be 1,500 per month or 50 rupees a day, which is a very affordable price for great quality education. Alright. So on top of that, if you get your subscription using my code RDLive, you get an additional 10% discount. So guys, quality education does not get more affordable than this. So get your subscriptions, give it a try. It's definitely worth the pricing. Alright. So you can also join us through the Telegram app with the link shown above. If you join us on this app, you will get notifications of all the lectures and future schedules. Alright. So moving forward, let's get started with today's topic. So today's topic is, again, as I said, this is lecture 2 of Work, Power and Energy, and today we'll be discussing about potential energy. Yesterday we talked about work, we defined work. Hello Pawan, how are you? So yesterday we defined work, then we talked about kinetic energy and we talked about work energy theorem. So work energy theorem, if you guys remember, said that the net work done by all the forces acting on a body is equal to the change in its kinetic energy. So today we're going to talk about some new kind of forces and the work that they show, and we will come to the realization that we need another concept, another kind of energy to be defined, which we'll call potential energy. Alright, so let's go ahead. So let's talk about another classification of forces which is called conservative and non-conservative forces. Alright. Now, careful observation will show that the behavior of forces, based on their behavior, they can be divided into two categories. These categories are called conservative and non-conservative. So let's go and take a look at few observations so that we understand this phenomena better. So imagine a block. So this block is right here it is projected with some speed u upwards. Alright, it is kept on the ground and we project this block of mass m vertically upwards. What happens? As it moves up, it slows down, eventually comes to rest at some point. Alright, so here your v will be 0. So how do you explain this phenomenon? Good evening, Ankit. How are you doing? So how do you explain this phenomenon? You say, okay, when the block was moving up, gravity, the force of gravity was acting downwards and it was doing negative work. Alright, so remember this, whenever a body does negative work, what will that mean? You remember work energy theorem told us that W equals delta KE. So negative work would mean that the kinetic energy would decrease and positive work would mean that the kinetic energy of the said body will increase. So in this particular case, we see that the force of gravity is doing negative work on our body, and because of which it is losing its kinetic energy, and finally the kinetic energy becomes 0. So when it has become 0, I realize how much work must have the gravity force done. It must have done a work of minus half mv square. Alright, so this is my situation 1. Alright, now let's talk about another situation. In the second situation, I have kept the same block in front of a spring. Alright, so initially the spring was relaxed. Now what I do is I give this an initial velocity u. So this block will end up compressing the spring, it will slow down and eventually it will come to a stop at some point and its final v will be 0. Now again I will notice that since it was pressing the spring was pressing it back. Alright, so spring during its whole journey ended up doing negative work on the block. As a result of this negative work, we can see that the block is losing kinetic energy, and by the time it comes to rest, it would have lost all its kinetic energy. So the work done by the spring from its initial position to the point where it comes to rest would also be minus half mv square. Alright, so this is my situation 2. So I realized, alright, in both the situations I see my block had a kinetic energy. Two forces, the force of gravity and force of spring, do work on it and take away all the kinetic energy from it by doing negative work. Good evening, Shrikant. How are you? Now, let's take about a third case. So, in my third case, the same block is kept on a rough horizontal ground and again given a speed u. So, it will move forward and eventually come to stop, right? So, how do I explain this? I will say that the force of friction did negative work, alright? So, friction will act in this direction and it is the force of friction that is going to do negative work on this, and eventually this guy comes to rest. Alright, so in these three cases we've seen one force doing negative work on the body and eventually taking away all its kinetic energy. Now so far the behavior of all three forces seems similar. Alright, they are all acting against the direction of motion and they end up taking away all the kinetic energy by doing negative work. Now the difference comes when we see what happens next. Alright, so let's talk about my case 1. So what happens next? Once it has reached its maximum height, now what happens? Now you realize it starts accelerating again and eventually it comes back. Alright, so it will come back finally and it comes back with a downward speed of u. So you realize what happened was that fine, the force of gravity did a negative work, took away all its kinetic energy, but then it starts moving forward. The gravitational force is doing positive work on it again, and by the time it comes back to its original position, it has gained its kinetic energy back completely. So the force of gravity can do negative work, take away the kinetic energy, but it can also do the positive work and give the energy back to the block. So which means, in the meantime, where did the energy go? Where did the energy go? We can say that for some time, the force of gravity stored this energy with itself, alright? And when it had the chance, when it got the chance, it can give the block this energy back, alright? Same thing will be noticed in the case of a spring. So when it comes to stop, what happens? The spring starts acting a force on it in this direction. The block ends up coming back to its original position and with exactly the same speed u, alright? So in this case also we see, fine, the spring did some negative work and the kinetic energy that it took while doing negative work, we can say that it stored it temporarily with itself. Now it is doing positive work back and it is giving the block its entire kinetic energy back. Alright, so you realize in both these cases, when the cycle was complete, when the blocks returned to their own positions, the kinetic energy which was taken away by these forces is completely given back. There is no loss of this energy. However, that is where this case becomes different, the third case. Now, once this has come to stop, there is no more, nothing that is going to happen here. All the energy that the force of friction takes, it ends up dissipating it away. All the energy that it took while doing negative work gets lost in forms of heat and sound and maybe light. And that entire energy is dissipated. It is not stored anywhere. Yes, Pawan, the work done in those cases in a cycle is always zero. So here we realize that some forces, when doing negative work, when they take up energy, they save it, they store it temporarily with themselves, and they have the ability to give it back to the object from which it was taken. While other forces, when they take up energy from any object while doing negative work, they do not keep it to themselves. They spend it all away. They dissipate that energy. Alright. So that is the difference between two kinds of forces. Now these forces, which are storing energy that they take away, they are called conservative. So both these kinds of forces are called conservative. Alright, why conservative? You realize there is absolutely no loss of energy. When the object came back to its original position, it was able to regain its entire kinetic energy. None of it got lost. However, what happens here? Here all the energy gets dissipated. Alright, so this is called a non-conservative force. So this does not store energy, this does not conserve energy, it ends up dissipating it. So these are also called dissipative forces. So that is our reason why we are dividing forces into these two categories, alright, conservative and non-conservative. So let's talk about the conservative forces now. So work done by these forces does not depend upon the path followed by the object. It only depends on the initial and the final positions. That is one thing that I realized. Alright. Let's try and prove that. And also you've been told that the work done by these forces along a closed path is zero, which we have already seen. When the object returns to its original position, what do I mean when I'm saying work done by a force along a closed path? So closed path means that the object is able to return to its original position. That is what I mean by closed path. Alright. So when an object starts from one point, let's say here, alright, it may move around anywhere, and if it comes back to its original position, then the path is called a closed path. Alright. So you will notice that in case of conservative forces, what happens is that the net work done in the closed path is zero. And as a result, you can say that the work done during two paths is independent of the path taken also. Let's see how that is. So let's take up an example. Let's say that a block starts from point A here and moves to a point B here, and it goes about a path, let's say like this. So this is how it went, and let's say the work done was W. Alright, and it comes back along another path. Alright, so it comes back along another path like this, and when it comes back, how much should be the work done? Since it has completed a closed loop, so the net work has to be zero, right? So if the net work has to be zero, that implies that the work done while coming back from B to A has to be exactly minus W. I hope you guys followed that. Right? Why is it minus W? Because in the closed path, the net work has to be zero. Right? Now these forces are a function of their speeds and positions, right? So whenever you realize, if I'm talking about the work done by this force, so if I'm here and if I'm trying to calculate F dot ds, so if it's moving in this direction, F dot ds and F dot ds when I'm moving in this direction will be completely opposite. Alright. Why? Because these forces have the specific thing that, again, think about this. When you've taken a small little path, then what happens? If you go here and the work done is dW, work while going back has to be minus dW. Again, why? Because of the closed path logic, right? For every small displacement also, if you go back, then you're forming a closed path, right? So if the work from coming here to here is dW, then the work from here to here would be minus dW. You realize that? So by that logic, I can say if the integral of f dot ds while going this way was minus w, what will be the integral of f dot ds while going this way? It will be plus w. Alright, I hope you guys followed this. So you will realize we have proven the fact that we were saying that the work done would be independent of the path. Even if it went through this path, let's call it path number 1, and when it went through this path, let's call it path number 2, the works have to be equal. Otherwise, the closed loop path would not come to 0. Alright, I hope you guys followed the logic. Please let me know. Let me know if you followed this logic. How we are proving that the work done would be independent of the path, using the fact that in a closed loop, the work done is 0. Okay, great. So, we realize two properties of conservative forces. One, the work done is independent of the path. Second, work done in a closed loop is always 0. Now, let's say a mathematical function of position can be defined for finding this work. Right? Why? Because we realize that the work done is independent of the path. So, it depends only on the initial and the final position. So, let's say, in general, most of the forces are given to you as functions of positions, right? So let's say I have a conservative force, and this conservative force is given to me as, I'm not writing the vector sign right now, or I may also write the vector sign, that does not matter. Alright, so I'm just talking about the magnitude right now. So it might be a function of x, y, z. So it's a function of its position. Now imagine when I'm trying to calculate the work done by a conservative force, what will it be? It will be this f, y, z times ds integral. Now when you integrate a function of x, the result will be a function of x, right? Similarly, when you integrate a function of y, the result will be a function of y. So let's say that this function, and let's say from position 1 to position 2, what does this give me? This gives me some other function. Upon integrating, I'm getting some other function of g. Alright, plus c. But I've put in the limits, so I'm getting this 1 to 2. Alright, so what do I get? I get g of position 2 minus g of position 1. Alright, now that we know that this is going to be independent of the path, which means every time I integrate along any ds, doesn't matter which, I should get this same mathematical function again and again. Why? The result has to be independent of the path. It has to depend only on the positions, which means upon integrating, doesn't matter along which path you're integrating, you should be always getting the same mathematical function again and again. Alright, this is what I mean when I'm saying that a mathematical function of position can be defined for finding the work by each conservative force, and this function is what we call eventually potential energy. This is the mathematical function that we are calling potential energy, by the way. Alright, so I hope you guys followed this. This is just a mathematical explanation. Alright, I'm saying every time you integrate f force, which is a function of position, along any ds, doesn't matter what ds, you obviously should get another function of position, right? And this function of position has to be the same function. You should be getting the same function again and again, no matter what path you integrate this function along. Why? Because the work done eventually has to be the same. So the work done is same. It doesn't matter along what ds I integrated, I should be getting the same mathematical function again and again and again. So this mathematical function, of course, is a function of position, and this can be used. Since I know I am going to get this particular mathematical function only again and again, I can directly remember this result and use this to calculate the work done by conservative forces. Alright, so that is the idea behind defining the potential energies. Alright, and that is how we get to the potential energy function. So these forces are called non-dissipative forces also. Why? Because they are not wasting any energy that they are taking. Alright, The examples of conservative forces are gravitational force, electrostatic force, spring force, etc. There are many more conservative forces which are possible. These are some examples. All right. So let's talk about non-conservative forces now. The work done by such forces depends only on the initial, does not depend only on the initial and the final positions, but also on the path followed by the object. You will realize that in case of friction, in case of kinetic friction, you will realize if a block was being dragged from here to here, the work done would be different if I dragged it along the straight line. It would be different if I dragged it like this. So it will depend on the length of the path also, right? Every time, why? Because I know in this direction, when I'm moving here, the kinetic friction is acting here. When I'm moving here, the kinetic friction is acting here. So what is the integral f dot ds? Integral f dot ds, if I assume that the angle between kinetic friction and displacement will always be 180. Why? Because kinetic friction always acts opposite to the displacement. Now, since it is kinetic friction, its magnitude has also to be fixed. Alright, its magnitude will not change. So while integrating this, I can get the f out of integration. And what do I get? Integral of ds. And integral ds is nothing but the path length. So I'm getting f into path length. So you realize here that the work done depends on the path done. This is work of friction. Alright, not only on the initial and the final positions, but the length of the path matters. Alright, that is what we can see clearly. Of course, there will be a minus sign here. Why minus? While taking dots, I will put cos of 180, so I'll get a minus sign also here. So, but I'll realize that here, obviously, the work depends on the path. Okay, then, there is a possibility that I may have another path which has exactly the same length. Right, so these paths, let's say this is path 1 and this is path 2. It is possible that two paths or maybe many paths may have the same amount of work, alright, just because all their lengths are same. As long as I keep taking the paths which are of same length, I will keep on getting my work as same, alright. But that should not lead you to a wrong conclusion. That should not lead you to conclude that this is a conservative force, alright. Why? Even though along many paths the work is coming out to be same. What happens when I form a closed loop? When I form a closed loop, the path length is not 0. Alright, it's still a positive number. It's the length of the path, even if I'm taking a closed loop. So that is a sure shot test for testing if a force is conservative or non-conservative. That the work done in a closed path will never be 0 for a non-conservative force. The work done by a non-conservative force may be same for two paths. That is just a matter of chance. But in a closed loop, it will never be 0. Alright. So since every time, now if I'm integrating this, you realize now if I'm integrating this, every time I'm getting a different result, which means every time the function that I get will be different. I am not getting the same function of position again and again. I'm getting different functions every time because the result eventually has to be the same. So one time it may be g of 2 minus g of 1. Another time I'm getting another function h, and my work is coming out to be h of 2 minus h of 1. So you realize every time the result of integration is different. Depends on the path. Alright, the moment I change my ds, I get a different result. So, which means I cannot define a mathematical function, constant mathematical function for this, for finding the works of this. Therefore, I cannot define a potential energy for these forces. These forces are also called dissipative forces. Reason that they end up dissipating energy. The energy that they take while doing negative work, they spend it all away. They do not store it. They do not save it. Alright. So examples of such forces are friction force, viscous force, and air drag. There are many more, but these are some examples. Alright, so why don't we get to some practice? Alright, so you've been asked that an object of mass m is pulled up to a height h using two different paths as shown. Find out the work done by gravity. Hello Sandeep. Yes, Pawan, of course I will explain graphs. In fact, I plan to do that tomorrow. Tomorrow I'll explain graphs, I'll explain different types of equilibriums, and I will talk about power. Because power is a very, very smallish topic, so tomorrow I intend to talk about all these. The graphs, UX graphs and their relations with forces, equilibriums, stable, unstable, neutral, and power. That is what we are going to talk about tomorrow. Alright, so let's talk about this. Yes, of course, mgh. And will it be plus mgh or minus mgh? Will be the work done by gravity. It will be minus mgh. PE is not conservative or conservative. Forces are conservative and conservative, Alok. PE is how you define the work of a conservative force, in fact. Yes, minus mgh. Potential energy is defined only for conservative forces. For every conservative force, you can define a mathematical function, alright, which will tell about its work. That mathematical function is essentially what you're calling potential energy. Alright, I hope you got that. See, what is energy? Energy is the ability to do work, right? So suppose this pen is kept here. So how much work can gravity do on it right now? It cannot do any work because it is not possible to displace this pen in the x direction, in the y direction. Alright, what happens when I pick this up and raise it up to a height h? Now, the moment I've raised it up to a height h, now you realize if I leave it, the gravity can do a work of mg times h on it, right? So here, what is the work that the gravity can do? Nothing. The moment I pick it up, now I have given the gravity a potential of doing mgh amount of work. You realize now gravity has the potential of doing up to mgh amount of work on it when I leave it. Okay, so when it comes down by h, gravity can do plus mgh work on it. That is what I am saying. That is what potential energy is. I have given the force of gravity a potential of doing some work. So that is what potential energy is. Hello Ganesh, how are you? Alright, so in both these cases, while taking up, the gravity did minus mgh, which means it took out mgh amount of energy. So that is the potential that it can give back also eventually. Alright, so that is why I'll say when I've picked it up, the potential energy would be plus mgh. Alright. Okay, so this was simple. Let's try another problem. An object of mass m is moving along a circular path of radius r over a horizontal plane. If friction coefficient between the object and the plane is mu, find out the work done by the force of friction during a complete cycle. So what will be the work done by the friction when it completes one circle? So an object of mass m is being moved along a circle of radius r. You define the work done by the force of friction when the object completes one circle. Thank you, Pavan. I appreciate the support. I would want more and more students to benefit. Of course, that is why I moved to online coaching. In fact, no, it will not be zero. No, no, it is not zero. Okay, let's see. So this is a block. It is being moved in a circle. See, friction is a non-conservative force. It will not have zero work. So imagine when it is being moved here by a small ds. Where will the friction act? I've shown you this before. Friction will be acting here, and friction will be kinetic. So it will be mu mg, right? So what will be F dot ds? So let's say F friction. I can say that dw would be F friction dot ds. So when I do the dot, what do I get? The force of friction, magnitude of force of friction, which is mu mg times ds times cos of 180. Now you realize, anywhere I go, even if I'm here, I get the same expression, right? When this moves here by ds, the force of friction, kinetic friction, would be acting in this direction now, right? So when I'm trying to integrate this to find the work, so work would be integration of this. So while integrating, you can take mu mg outside this integration. Why? Because this is a constant, and this cos 180 will become a minus, and all you have is integral of ds. What is integral of ds? ds was length of this small displacement. So if I keep on adding all these small displacements, what will I get? I'll get the circumference of the circle. Alright. So I'll get my work as minus mu mg times 2 pi r. That will be the work done by the friction when it completes one circle. Not zero. This is a non-conservative force. It will have a non-zero work in a closed path. Alright. I hope you followed that, Pawan. Guys, did you follow this? What we did and how we found the work done by friction? See, every time for any small displacement ds, the angle between F and S is going to be 180 always. Similarly, the magnitude of F is always going to be mu mg. Good. So that is how you solve it. Okay. Alright, now let's talk about potential energy. I already told you that what we are doing is we are trying to find a mathematical function which can help me calculate the work of a conservative force again and again. Because I know since this is going to be a fixed function, so why not learn it so that we don't have to calculate the work of conservative force again and again. That is what we are trying to do. So remember the definition, how we define potential energy. Potential energy was defined as the energy possessed by a body by the virtue of its position. Why position? It is a function of position, okay? And that is what we call potential energy. So for every potential energy comes from a conservative force only. So the potential energy is the energy that the conservative force has stored, or the potential of work that a conservative force has to be able to do work on the body. So whenever I'm talking about potential energy of the body, so suppose if I have a spring and if I have a block and if I press this block against that spring, so I know I have given the spring an opportunity, a potential of doing half kx square amount of work on this block by the time it comes back to its natural length. So that is the amount of work it can do on the object. Alright. So that is what we call potential energy. It is the potential amount of work that a conservative force can do on your object. Alright. So that is why every potential energy eventually comes from a conservative force. And hence it is defined only for conservative forces. You cannot define potential energies for non-conservative forces. Okay. Now, as work done by conservative forces depends only on the initial and the final positions. That is why the potential energy also depends on the positions. It will depend only upon the position. Alright, now let's see mathematically how we get it. So mathematically what we do is we define the change in potential energy of any object from moving from position R1 to R2 as minus times work done by a conservative force. You remember now, I told you, if the spin is here, the force of gravity cannot do any work on it right now, right? So when I move it up by h, so while I moved it up by h, what was the work that the force of gravity did on it? Minus mgh. So since it took away minus mgh, or it took away mgh amount of energy, when I have got it here, I can say that the energy that the conservative gravitational force has stored with itself is mgh. So whenever a conservative force does a negative work, it stores that energy. So negative work means I'm taking energy from someone. So whenever a conservative force is doing negative work, means it is taking energy from somewhere. And whenever it takes energy, it still stores that energy in the form of potential energy. And that is what we say. That is why we define delta U as minus times WC. So whatever negative work a conservative force will do, we'll say that by this much amount, its potential energy has increased. Alright, it has. Yes, I have uploaded the notes. I think the team will be putting it in the download link also. Don't worry. So that is what I mean. That is how I can define potential energy with the help of work done of a conservative force. I can always define, hi Kushal, how are you? I can always define delta U as minus times WC. So whenever a conservative force is doing some negative work, it is increasing the potential energy. It is storing it with itself. So we say that the potential energy due to that conservative force increases. Okay. So remember that. So mathematically, we would define delta U as minus times work done by conservative force. See, this is what? This is work done by a conservative force while going from R1 to R2, position R1 to R2, right? So you realize F is your conservative force. So this is the relation between a delta U and work done by a conservative force. Oh, I'm always great, Kushal. Thank you for asking. Now, remember, the potential energy of a property is the property of an entire system responsible for the conservative force and not property of any specific particle or object. What do I mean by that? So when you're saying that this pen is lifted upwards. So what is the conservative force? The conservative force is the force of gravity. How is the force of gravity coming from? Where is the force of gravity coming from? It is coming from the interaction between this pen and earth, right? So the potential energy is not solely the property of the pen itself. It is a property of both. It is actually available to both the earth and the pen. Alright. So when you are in space, let's suppose, and if you have two masses kept in front of each other, you realize they are having a force of gravity on each other. If I just release one mass, it will get attracted. It can gain kinetic energy on the expense of that potential energy. Similarly, if I keep this holding and if I release this, then this can also gain kinetic energy at the expense of that potential energy. The potential energy that is stored in the force of gravity, which they are exerting on each other. If I release both can gain the kinetic energy at the expense of that potential energy. However, we know that when we are talking about the pen and the earth, when I release this, most of the kinetic energy is going to go to the pen only. Why? Because of the huge mass of the earth. It will hardly feel any acceleration due to the force of gravity of this pen. Alright, so because that we ignore the kinetic energy that the earth may be gaining. That is why in common examples we say, okay, the pen has gained this much of potential energy. But actually speaking, technically speaking, it's not the pen that has gained mgh amount of energy. It's the system of pen and earth both who have got this potential energy. Alright. And both of them could have gained kinetic energy on the expense of this. Okay, so let's talk some more about potential energy. Now, as I said, I have already defined mathematically that delta U equals minus times WC. So I can always define a function, mathematical function, which is giving me the change in potential energy. What happens if I want to define absolute potential energy? So what does that mean? That means that when I'm defining it like this, let's say I am bringing an object from position 1 to position 2. Alright, so delta U would be U2 minus U1. Alright, and this will be the minus times work done by conservative force in moving from 1 to 2. Alright, so I can always define the change in potential energy easily. Now, if I want to define an absolute potential energy, absolute value of potential energy, then what we do is we take some random position as a reference point. So I will choose any random position. That is completely up to me. Alright, I can choose any random position and I can say, okay, I will consider the potential energy to be 0 here. So that is what I mean when I'm saying that we need a reference point. We choose a point where we say, okay, I will consider that the potential energy here is 0 and that will become my reference point. And when I assign a 0 value to one point, now I have absolute potential energies of different points. Alright, but again, the absolute potential energies do not matter. Why? The absolute potential energies will depend upon your reference point and different people can take different reference points. So though there are some commonly accepted reference points, but it's not a compulsion. You can choose to change that reference point and trust me, there is nothing wrong with it. However, the choice of reference point will never affect your answers. Why? In most of your answers, what you're trying to find? You're trying to find the work. And work is related to potential energy as change in potential energy. And change in potential energy between two positions will be independent of your reference point. Doesn't matter which point you choose as 0. When you're talking about two positions and change in potential energy from when moving from here to here, it does not matter where you kept your 0. For instance, let's say, you realize most of the time we take the ground as the 0 level for potential energy, right? So if I take ground as my 0 level for potential energy, then when the object moves up to a height h, now I say its potential energy is mgh. However, I could have done the other way around also. I could have taken this as my 0 level. So if I take this as my 0 level, then I could have said the potential energy here is 0, and in that case, the potential energy here would be minus mgh. Right? There is absolutely nothing wrong with that. You can choose your 0 reference point freely. You're free to do that. And you realize whenever you do that, the change in potential energy is still the same. So when you're taking this up, the potential energy in this case increased from 0 to mgh. So the change in potential energy was plus mgh. Even when you move it from here to here, you realize the potential energy changes from minus mgh to 0. So the change is again plus mgh. Alright. So you remember many a times we do this. A table is there, a chain is hanging, and you have to find the speed of this chain. Right, so in those cases, you can take this as your 0 point also. So you can choose any point as your 0 point for potential energies. All right, so that is not a restriction. But the point is that you have to choose a 0 point in order to specify the absolute value of potential energy. All right, without that reference point, you can only talk about the change in potential energy. To give an actual value, okay, the potential energy at position 1 is, let's say, 5 or 7. To define it like that, I will need a reference point where I will assume my potential energy to be 0. Okay, so remember that. So as I said, we need a reference point to define absolute values of potential energy. Absolute potential energy of any object is defined as the negative work done by the conservative force in moving the object to that point from the reference point. Hello Akash, life is all good. Don't know. All good, all good. So once you have, suppose once I say, okay, position 1 is my reference point. Hello Harshu. So once I've decided, let's say position 1 is my reference point. So I can say if position 1 is my reference point, I will say that u1 is 0. So if 1 is chosen as reference point, then I can say that what is choosing a reference point means that I am saying that the potential energy there will be 0. Now you realize if I substitute these things in this equation, then what will I do? That potential energy at any point P then would be P potential energy at P minus 0. Why 0? U1 will become 0. U1 is potential energy at point 1, which I have taken to be my reference point. So I know U1 is 0. This will be equal to minus times work done by conservative force in bringing it from position 1 to position P. So that is how, once I have chosen a reference point, I can define the absolute potential energy of any point P as the minus times amount of work required to bring my object from its reference position to the given position. Alright. So why don't we take a look at certain examples of potential energy functions. Alright, so I already told you. In mechanics, we mostly deal with two potential energies. Alright. So gravitational potential energy, which we take as mgh, and why are we taking it as mgh? So most commonly we take the ground as the reference point. So if I'm choosing this as my reference point, so this is my u equals 0 point. So let's say if I have a point which is at a height h above this, so what is the u going to be here? I can say that use my expression u minus 0 should be equal to minus times work done by gravity. And what is the work done by gravity? Work done by gravity would be minus mgh. Why? The entire duration, the force of gravity is acting downwards and I'm displacing the object upwards. Okay, so the work comes minus mgh. So I realize u now at a height h can be defined as mgh. So that is going to be my function of gravitational potential energy. U at any height h above the ground is mgh, and of course I have to mention here reference point is ground, and h is height above ground. Alright, only then it is mgh. Okay, so remember this. Similarly, what about the spring potential energy? Alright, so I'm getting rid of this. So if you talk about spring potential energy, now for that what we do is we take the relaxed length of the spring as our reference point. So suppose you have this, and this is the relaxed length. Alright. And suppose you are pushing it by a distance x. So it comes here. Alright, so let's see what is the work done by the force of spring when I have pushed it certain distance x. So let's consider an intermediate position. Somewhere in the middle, it was pushed, moved from here to here. So it was already pushed by some y, and I'm pushing it by another small dy now. So I push it by a small dy from its position y. So when it is pressed at y, will be the spring force. Spring force would be minus ky. Alright. So spring force is minus ky. What will be the work done in displacing it slightly? Alright. Again, now while taking the dot, I will not take the minus sign because I have already taken the minus sign with the f of spring, which is denoting that the direction is opposite to that of the displacement. So ds is dy. So dw would be minus ky dy, and I need to integrate this from 0 to x. Why? Because 0 compression I have taken as the reference point. So I will realize that my work in moving from 0 to x comes out to be minus 1 by 2 kx square. Alright, and by definition, u at x minus u at 0 would be minus of this. So it will be half kx square. Alright, and ux0 has been taken to be 0. This is my reference point. So what I know is that u of x equals half kx square. Now you will realize this will be the same expression even for elongation. Yes, Pawan, well said. So that is what we define our potential energy, spring potential energy function as. We define u at x being the elongation or deformation equals half kx square with x equals 0 as reference point. Please remember. So if I generally ask you, what is the potential energy of any object? You should not be answering that unless I have told you what the reference point is. Now, usually in cases of springs, it is understood. But please remember, please be careful. I mean, IIT Advanced, they do this. They will ask you such conceptual things. Alright. They may just give you a question. A spring is compressed by X. What is its potential energy? What is the potential energy stored in the spring? And the choices may say half kx square, and it may say half kx square only when the reference point is taken at x equals 0, and it may say if x equals 0 is taken as say point of 2 joule energy. I mean, I can assign any energy on x equals 0. So I can even say at x equals 0 it has 2 joules of energy. In that case, u at x will become half kx square plus 2. So remember this, because this is the change in potential energy. So if u at 0 is defined as 2, then you will realize from here the 2 would have gone on that side and the potential energy at x would have become half kx square plus 2. So remember this always. So you're using only these functions under the assumptions that these are the reference points. If you change your reference points, then you cannot use these functions for your potential energies. Now, other commonly used potential energies include elastic potential energy and electrostatic potential energy. But we will talk about those later when we get the use. Right now in mechanics, as far as Newton's laws are concerned and all your work power energy calculations are concerned, mostly you only talk about two kinds of potential energies: gravitational potential energy and spring potential energy. Spring is put at a height h. Will it also have gravitational potential energy along within its potential? Yes. As I said, every conservative force will have a potential energy. All right. So if you have a situation where your spring is like this, so this block will have two kinds of potential energies. There will be potential energy stored in the spring, and there will be potential energy stored in the force of gravity. So this system will have two kinds of potential energies. All right. So the total potential energy of this kind of system will be a sum of the potential energy stored in the spring plus the potential energy stored in the force of gravity. Alright. The potential energy here would be sum of two PEs, spring PE and gravitational PE. You have to take all the PEs into account while writing the total potential energy. So remember this. If tomorrow there is a situation where there is also electric field, then there might be also electrical potential energy. So when I ask you what is the total potential energy, then you have to report the sum of all three. The sum of gravitational potential energy, spring potential energy, as well as electrostatic potential energy. Alright. So remember that. Good you asked that. So now why don't we try an example. An object is under the influence of a conservative force which is given by as F equals AX plus BN, okay, where A and B are positive constants and X is in meters. Then find the change in potential energy when the object is moved from X equals 2 to X equals 4. Okay, so why don't we try this problem? You've been given your force as F equals AX plus B. Alright, you have to find the change in potential energy when you displace an object from X equals 2 to X equals 4 under the action of this force. So please find the change in potential energy. Okay, so this force acts along the x-axis only. We're talking about a 1D condition, by the way. So the force is a vector. Here it should be specified that this is only along I cap. And the displacement is also along I cap. Displacement along x-axis. See, this will also be a conservative force, by the way. You can test that. Alright. But right now I'm telling you this is also a conservative force. Even though it is a variable force, it is also conservative. Just like spring force. Spring force was a conservative force even when it was variable force. You realize this equation is very similar to the spring. You can assume that a spring is connected maybe here. So when this is getting elongated, the spring is acting a force on this. Or maybe the spring is on the other direction. Right. Or you're pushing it, I don't know. So it could be somewhere related to a spring, this kind of force. So why don't you guys find the change in potential energy? Please do this quick. Use the equation delta U equals minus times WC. Use this expression to find the change in potential energy. Alright, hurry up. Okay, so that seems about correct. Yes. Yes, minus times that. Very good, very well done. So F was given to you as AX plus B. You know, to find the work done, what you need to do. Work done would be AX plus B times dx, and we need to integrate this from 2 to 4. Alright, so work done would come out to be AX square by 2 minus BX from 2 to 4. So this comes out to be A over 2 times 16 minus 4. So check your coefficient for A, Pawan. I think you got that wrong. Alright, so this is what your work is. So your work is coming out to be, this is 12, 6A minus 2B. Alright, so delta U of course would be minus times, or I can simply say plus 2B minus 6A. So that will be your delta U. We use the fact that delta U has to be minus times work done by the conservative force. So Pawan, please check. I think you forgot this 2 here. Check your calculations. You forgot that 2 here while integrating x. Integration of x is not x square. It's x square by 2. Remember that. Alright. So Pawan, did you find your mistake? Please let me know fast. Did everybody follow the solution? Just let me know quick if everybody followed this, how we calculated the change in potential energy. Just let me know quick. Oh, okay, so there'll be a plus here. Okay, one small mistake that I made was, yes, it'll be, okay. Yeah, I don't know why I put a negative sign here. It'll be plus only. So plus here. So minus times 2b plus 6a. Yeah, that's right. Now, I don't know how I put that minus sign there. So that is it, sorry. That is going to be the answer. Alright, so I hope this is clear to all. Let's move forward. Let's take a go at another problem. Alright. So this problem says that a block of mass 5 kg is moving with a speed of 4 meter per second. Find the kinetic energy of the block in the ground frame, in the reference frame, and in the reference frame. Okay, I think we had already done this yesterday. Oh, this is yesterday's problem. I think I forgot to delete this slide. Alright, so let's talk about the work energy theorem one more time. So remember, yesterday we wrote our work energy theorem as the net work done by all the forces is equal to delta Ke. Remember? Right, so today we discussed that all these forces can be divided. This work can be divided into two parts. Why? Because all forces can be divided into two parts. So I can write this net work in two parts. Work done by non-conservative forces plus work done by conservative forces. Alright, so I can rewrite the equation of a work energy theorem which said the net work done by all the forces is equal to delta Ke as work done by non-conservative forces plus work done by conservative forces equals delta Ke. Now if I rearrange the equation, I can also say work done by non-conservative forces is equal to delta Ke minus Wc. And we already know that what is minus Wc? Minus Wc is delta U. Therefore I can write my work energy theorem again in the form that work done by non-conservative forces is equal to delta K plus delta U. Alright. Right? I hope everybody followed this. So this is how I can write work done by a non-conservative force. Now this relation is another form of work energy theorem only. Alright, here instead of taking the net work done by all the forces, on the left hand side of the expression, I am taking only the work done by non-conservative forces. So work done by non-conservative forces will be equal to delta Ke plus delta U. You also know that the sum of the kinetic energy and the potential energy of an object are known as its total mechanical energy. Alright, so remember this. The sum of the kinetic energy and the potential energy of any object is called the total mechanical energy. Now let's go over a special case. And this special case will yield to a special result called conservation of mechanical energy. So as we realize that work done by all non-conservative forces is equal to delta K plus delta U in a special case where all non-conservative forces are absent. Suppose there is no non-conservative force in the system, or even if they are, they're not doing any work, suppose. So in that particular case, what will my equation become? My equation will become delta K plus delta U equals 0. Now delta K can be written as the final kinetic energy minus the initial kinetic energy. So why are there two types of charges and only one type of mass? Sir, explain. But I didn't understand. Please explain. That is what we have observed, Akash. That is just an observation that we have. The charges are of two types and they tend to cancel each other out. That does not happen with masses. Masses are only of one type. That's just the fundamental property of nature and that is how it is. I don't know how somebody would explain that. There is no explanation for it. It is just a fact which we have observed. Alright, our experiments show that that is what that it is. I mean, you can say, why only mass? Why does it have mass? Why does it have charge? Why only two types of charges? Why not three types of charges? I'm not sure what he told you. I don't think that there is any explanation for this. I mean, why not three kinds of charges then? Okay. Why not five kinds of charges? Why only two kinds of charges? What is the explanation for that? Right, Akash? Why only two kinds of charges? If there can be more than one type of charges, why only stop at two? Why not three? Why not five? What is the explanation for that? Yes, there are no three charges because that is what we have figured, we have realized. In whatever experiments we did, we only found two types of charges. We never found a third type of charge. If we had found a third type of charge, we would have said charges are of three types. Alright. So there is no reason for that. I don't know how can somebody tell you a reason for that. Alright. Just that there are two types of charges, and since they tend to cancel each other out, that is why we call them negative and positive also. Remember, it's we who are calling them negative and positive. They don't know that they are negative and positive. In fact, an electron does not know, okay, I am carrying a negative charge. It does not have a label on its head saying negatively charged. That is what you are calling them. Alright, you notice their behavior, you started calling one negative and the other positive. You could have called electron positive and the proton negative also. Okay, do let me know the reason when you know it, because I would love to know it too. Okay, so why don't you ask for that reason again and let me know as well? I would be interested myself to know the reason. No, Rakesh, electrostatics is not completed. We are in fact talking about Gauss law right now, and at 6 o'clock I'll talk about the applications of Gauss law. Alright, I don't know, Akash, he may have given you some weird explanation. I don't know, but I don't think there is any explanation for that. Alright. Theoretically, there can be negative mass. Theoretically, there can be. Why not? There could have been a negative kind of mass, but practically we never saw it. No problem, Baba. Right, Akash? So I don't know what explanation has been given to you. Please share it with me. I am more than curious. All right. Do you know there is something called dark matter? Again, that is something which experiments show that there might be something, because a lot of observations in space are not being explained with the help of normal theories. So we have come up with something called dark matter also to explain what we observe. So whatever Akash you are seeing, yes, it all comes out from what we observe in experiments. We do experiments, we make observations, then whatever observations are consistent, based on that we come up with a theory to explain it. So whatever experiments or observations we did about mass is only of one kind. It always behaves one way. Okay, it always exerts a force of gravity. It always attracts other masses. Alright, while charges, they were behaving differently. Some charges repel some charges and some charges attract other charges. So if all the charges were of one kind only, then they would have either repelled all the other charges or attracted other charges. Since sometimes they attract some charge, sometimes they repel some charge, that is how I know that there are two kinds of charges, because of observing their behavior. Alright. There is no explanation as to why there are two kinds of charges and only one kind of mass. You realize, even the mass, even the word mass we have assigned to it. Even the word charge we have assigned to it. What if the property that we call mass, somebody while named that as charge, and what we call charge right now, somebody named that mass, then you could have said, okay, masses are of two types, plus and negative, and charge is of only one kind. See, the name does not matter. The name does not matter. What matters is the property. You could have given any property any name. That was completely up to you. That was completely up to the guys who were deciding for the first time. Okay, glad. But do let me know the explanation you were given, because I would be curious to know. This is the first time I'll come to know why there are two kinds of charges and why only one kind of mass. I would want to know myself. I'm sure if Newton was alive, he would want to know himself. Anyway, so as I said, if you look at this equation and take a special case where either there are no non-conservative forces, or the non-conservative forces, even if they are present, are not doing any work, in that case this becomes 0. Yes, absolutely. But you just have to convince everybody else to start calling electrons Akash. Then we would say that every atom is made up of Akashas, protons and neutrons. You just have to convince everybody else also to start calling electrons Akash. So similarly, what you're calling charge and what you're calling mass does not matter. What matters is the behavior that we observed. Alright. So anyhow, if there are no non-conservative forces present, then this comes down to 0, which means my equation becomes this, and I know delta K can be written as K final minus K initial, and delta U can be written as U final minus initial. If I rearrange the coefficients, then I can say that K final plus U final is equal to K initial plus U initial. Or in other words, I can say that the total mechanical energy of the object remains conserved. You realize I did not decide when is my final and when is my initial. I can take any one moment as initial and any other moment as final. So between any two moments, in case there is no non-conservative force present, then between any two instants, the sum of kinetic and potential will remain the same. The sum of kinetic and potential energy we call total mechanical energy. So we can say that in case of absence of non-conservative forces, the total mechanical energy of a body remains constant or conserved. Now, please remember that this conservation of mechanical energy is only valid when the work done by non-conservative forces is 0. So, before you apply conservation of mechanical energy, you need to check whether this condition is getting satisfied or not. You do not blindly apply conservation of mechanical energy in all cases. So, that is another mistake that I've seen students make a lot. So please remember this, that only apply conservation of mechanical energy in the absence of non-conservative forces, or make sure no non-conservative forces are doing any work. Alright, so why don't we practice a problem using this? So you've been told an object is dropped from a height of 10 meters. You'd find the velocity just before hitting the ground using conservation of mechanical energy. Alright. Yes, that'll be great. Thank you, Akash. I would also love to learn something new, something that I didn't know yet. Okay, so how do we do that? This is simple. So you've been told that a block is dropped from a height of 10 meters. So you take this as position 1, you take this as position 2, and you'll for run now I can take this as my reference point to be U0 point. I'm taking this as my reference point. Initially U is 0. Finally, whatever is V, that is what we are interested in finding out. Alright, so what I do is I will write my K initial. So what is my K initial? It is 0. Why? The object is at rest, U is 0. What is my U initial? Initial potential energy also 0, because I've taken this as my 0 point. Let's talk about my final kinetic energy. Final kinetic energy can be written as half mv square. And how about my final potential energy? Final potential energy I can write as minus of mgh. Why? Because the object has come down by h. Alright, so it has come down from the 0 point. So when it comes down, I know the potential energy changes by negative. So now you can apply conservation of energy, and you can say half mv square minus mgh equals 0. M's get cancelled out. I get v as root 2 gh. And substituting the values, I have root 200, which is 10 root 2. Alright, so this we solved without using any acceleration equations, without using anything else. We just applied conservation of mechanical energy. Yes, Pawan, well done. Alright, now let's try and do something very interesting. Alright, using the conservation of mechanical energy. So two masses are hanging from a pulley as shown. Find the acceleration of the two masses using conservation of mechanical energy. So this is the classic Atwood problem, alright. Wherever you see this problem, they always solve it using F equals ma equations, right? Now today what we are going to do is, we are going to solve this equation. We are going to find the accelerations of m1 and m2 without using a single F equals ma equations, just with the help of conservation of mechanical energy. Alright. So let's see how. Okay, so let's redraw the situation slightly. So I am saying that, okay, here's my pulley, here is M1, and here is M2. So this is M1, this is M2, and I'm assuming that this is my position 1. Initially, both the blocks are at rest. Alright, so U1 is 0. I'm assuming U2 as 0. Okay, so both were at rest. Oh, by the way, these U's are small U's, so they are speeds, not velocities, or not potential energies. All right. Similarly, let's for this for right now take this as capital U equals 0. So I'm taking this as my reference point for potential energy. All right. So I'm assuming initially both the masses were here and both of them were at rest. Now, so this is my position 1. All right. So this is position 1. Now let's talk about position 2. Let's assume both the masses started moving and this guy came down by a distance x after some time. Alright. Now since this guy came down by a distance x, what must have happened to the other guy? It would have gone up by a distance x. Agreed. Also, let us assume that at this instant your m1 is moving with a speed v downward. Then obviously, because the two masses are connected with the string, this guy must be moving with a speed v upward. So this second instant I'm calling my situation 2. Now, while this entire motion is happening, is there any non-conservative force which is doing work? No. Tension never does any net work. So tension, though, is not a conservative force, but tension never does any work. So in this situation, we realize work done by non-conservative forces is 0. Alright. And since the work done by non-conservative forces is 0, we can apply work energy conservation, mechanical energy conservation. Alright. So, let's start writing our energies. So, what is K initial or K1? K1 would be 0. Why? Because both the masses were at rest. Okay, U1 was 0, U2 was 0. What about U1? Both the masses are at the 0 reference level only for our M2. No, that's not the answer. That's not the answer, Pawan. So U1 will also be 0 for both the blocks. Alright. So these are our condition 1. Situation 1, I can write my K1 as 0 and U1 as 0. How about my condition 2? In condition 2, I can write my K2 as half M1V square plus half M2V square. Why? In my situation 2, I will realize that both my masses are moving with the speeds V, right? So this will be my kinetic energy in situation 2. What is the potential energy in situation 2? Let's see. This mass has come down from the reference point by x. So this will have a potential energy of minus m1gx. And what about the other mass? It has gone up from the reference point. So that will have a potential energy of plus m2gx. Right? I hope everybody follows this. My both initial kinetic energy and initial potential energy will be 0. Why? Because both the masses were at rest and both the masses were on the 0 reference level of my potential energy. In my K2, I realized both the masses, situation 2, I realized both the masses are moving with V. So the final kinetic energy would be half m1 v square plus half m2 v square. How about the potential energies? Mass m1 has come a distance x below the reference level. Since it has come down, so its potential energy would be minus m1 gx. Mass 2, m2, has gone up by a distance x from the 0 point, so its potential energy would be plus m2 gx. So this is what I can write. Now I use energy conservation. So using mechanical energy conservation, what can I say? That k1 plus u1 should be equal to k2 plus u2. So I can write half of m v1's half m1 v square plus half m2 v square minus m1 gx plus m2 gx equals 0. So I can also write v square by 2 times m1 plus m2 equals, here I am taking gx common, m1 minus m2. Now we just need one step. Just differentiate both these sides with respect to time. Alright. So differentiate both sides with respect to time. So when you're differentiating, obviously these two are constant. The only thing that will get differentiated is v. So what is the differentiation of v square? And with respect to time. So with respect to time, when you try to find out, it will be half m1 plus m2 times 2v times dv over dt. Alright, that is the derivative of the expression with respect to time. Alright, how about the other side? Again, g is constant, m1 minus m2 is constant. The only derivative would be dx over dt. Okay, I hope everybody follows this. Alright, so let's just rewrite things. Alright, so I'm writing the result here one more time so that it is clear. Half of m1 plus m2 Thank you, Ankit. My favorite part of physics is mechanics. So this was the expression that we got after differentiating. Now you will realize what is dv over dt. dv over dt is nothing but acceleration. Similarly, what is dx over dt? dx over dt is nothing but v. I can cancel these out, and what I am left with is m1 plus m2 times v times a equals m1 minus m2 times g times v. This dx by dt is v, this dv by dt is a, right? So you will realize both the v's get cancelled, and what you get your a as m1 minus m2 over m1 plus m2g. Now you can use your Newton's equations, F equals ma equations, and you will get the same answer. Great, it is one of the most interesting topics of physics, of course. And the variety of questions is so huge that you have to use a lot of brain while solving mechanics problems. Dear Australians, this is a topic for 11th, but then as I said, the series is meant for 2020 aspirants. So I'm not having every discussion right from the scratch. I'm not going through the derivations of things. I'm just doing it very, very fast. Okay, so when I discuss this for class 11th, I will take it very, very slow so that you understand everything. So did you follow this solution, Pawan? Here we just used conservation of energy and solved this pulley problem without using a single F equals ma equation. See, that is the power of work power energy tool. It is a very powerful tool. See, what's the difference? You can solve any problem of mechanics using Newton's laws. You can also solve them using work power and energy also. You give me any problem of mechanics, most of the problems can be solved using both. The advantage with work power and energy is that Newton's laws, you know, Newton's laws has vector equations. F equals ma was a vector equation. So when you are solving problems with Newton's laws, you are dealing with vector equations, which might be tough at times. And work energy power has scalar quantities or scalar equations to deal with. And you know it is easier to deal with scalars than to deal with vectors. You've been studying scalars since your childhood. You've been studying scalar quantities. You only started studying vector quantities from class 11th. So this will provide an alternate, easier approach where you just have to deal with scalars and you can get to your answers. Alright. So alright, in this situation you may not find a great utility. You may think, okay, this is almost the same amount of work that was needed in solving the problem with Newton's laws. Absolutely. I just wanted to show you that any problem that you usually solve with Newton's laws can also be solved using conservation of energy. The advantage is not very distinct here, but in many cases, trust me, this method will be way easier and way advantageous than your Newton's laws. Alright, so next time we will go over some more problems where we will see the applications, some more applications of conservation of energy. Alright, thank you so much, Pawan. Alright, so that is it for today. I would like to wrap it up today, and why don't you guys go ahead and solve some problems, alright, based on conservation of mechanical energy, and let me know how it goes. Tell me if you find any difficulty. So just remember, whenever you have a problem, you see if there are non-conservative forces acting, if you see if there is work done by non-conservative forces or not. If you have work done by non-conservative forces, please remember. So your problem solving strategy will be, first check. So let me just write it down quickly. Let me just write down some problem solving strategies. So let's do it here. So what are the problem solving strategies using work energy and kinetic and potential energy? So let's just go over it quickly. Problem solving strategy. So first, okay, later. First, identify, okay, what am I writing? Identify an initial situation and a final situation. So that is what you will always do. You will take some situation as your initial situation and final situation, and some situation as your final situation. So depending on what has been given to you and what has been asked of you. So wherever, in whatever situation you've been given things, that can be your initial situation, and wherever you have been asked to find out, that can be your final situation. Alright. So you identified your initial and the final situations. Now identify identify non-conservative forces, if any. Next is that you will look for non-conservative forces. Thank you, Bhiku. So next you identify if there are any non-conservative forces. If yes, you use the equation work done by non-conservative forces equals delta K plus delta U to solve your equations. If no, then you use delta K plus delta U equals 0. So that is how simple it is going to be solving problems using work energy theorems. So see what has been asked to you. According to that, decide an initial situation. What has been given to you, decide an initial situation. What has been asked of you, decide a final situation. Once your initial and final situations are decided, now go through the process of moving from initial to final. So while the object moves from its initial position to its final position, see if are there any non-conservative forces which are acting on the body. If yes, then we will use this equation. We will find the kinetic energy and the potential energies at the initial and the final positions. We will also find the work done by the non-conservative force during this motion, and we will apply this equation. And if there are no non-conservative forces acting, then we will use this equation. We will simply find the initial kinetic and final initial kinetic and potential initial kinetic and initial potential energy, then final kinetic and final potential energy, and use conservation of mechanical energy. All right. That is not a problem, Pico. Yes, I am here to help students. Uh, so that is what I can do at my end, right? So let's see if students want to study some good content, want to understand their subjects well. See, my aim is, that was one of the reasons that I took up teaching also, by the way, Pico. That, even in my college, we'd never had many good teachers. I shouldn't be saying this. All right. So, and a lot of times I heard this from my juniors that their teachers were not good. And I know from personal experience also that a lot of teachers, people are not getting the physics right. All right. And I love physics so much that I want people to understand physics properly and get their concepts right. I don't want them to be misinformed, misguided. And students lose out because of that, which I find is unfair. That student is not able to perform well just because he was not guided well and he was misguided. All right. So, yes, so I enjoyed teaching the right concepts and the right physics so that you can understand physics, love it, and do well in your exams. And yeah, it's always good if more people would participate. But in any case, whoever is watching, plus this video remains at the on the channel. So I'm sure if people did not watch it right now, they will watch it later, so they can use this later also, and I'll be glad to help. All right. Yes, you can do that. Thank you for the support, Pawan. So that'll be it for today's discussion. All right, now before I leave, let me remind you, you can get your Unacademy subscriptions by following easy steps. You install the app. Once you've installed the Unacademy app, go to the plus segment, select your goal as IIT JEE and click on get subscription. All right. So when you're getting subscription, don't forget to use my code RD Live to get your subscriptions. You use my code and you will get additional 10% discount. All right. Thank you, Baba. If you liked today's video, if you think you learned something new and it helped you, then please press the like button and share it with your friends. Also, don't forget to press the bell icon and get all the notifications of future lectures. All the PDF of all the slides used in this lecture will be available for download by tomorrow. So tomorrow you can come back to the video, check out the description box. The download link will be available there. It would be great if everybody, if at least teachers, try to learn the right things instead of just saying wrong things in front of students. Anyways, that's slightly unfortunate that some people tend to do that. Okay, so don't forget to join us through the on the Telegram app using that link shown above. All right. So again, before I leave you guys, my code is RD Live. You get 10% off using this code. So I'll see you guys tomorrow, and tomorrow we'll discuss about the relation between conservative forces and their potential energy functions, and we'll discuss about the graphs and different kinds of equilibriums and power. So tomorrow we'll try and wrap this work, energy, and power chapter. All right. So please do join me tomorrow at 4. All right. Till then, bye bye and take care.